This is my Calculus 1 course. Today we're going to learn the most important application of calculus. We're going to learn how to find what are referred to as maximum and minimum values of a function. If you haven't done the homework completely and correctly from the last class, do that homework before watching this video. An absolute maximum value of a function is an output of a function, or y value of the graph of a function, that is greater than any other output of the function. So if we think about it in terms of the graph of the function, an absolute maximum value of a function is the biggest y value. It's important to understand that the values of a function are the outputs of the function, the y values of the function. So an absolute maximum value of a function is the biggest y value. So this is the absolute maximum value of the function. Now, we also have something called local maximum values. Local maximum values are y values that are bigger than any other y value of the points near that corresponding point. So this point has a y value that's bigger than the y values of the points around it. So it's called a local maximum value. But it's not the biggest y value of the function. So we call it a local maximum. Also, we use the term relative maximum. So as you can see, the concept here is pretty easy. Now, it's important to understand that an absolute maximum can also be referred to as a local maximum. So you see this y value here, that's an absolute maximum, or that's the absolute maximum of the function. But it can also be called a local maximum because obviously this point has a y value that's bigger than the y values of the points around it. Also, mathematicians have decided that endpoints cannot be local maximums or minimums. We'll talk about what that means later on. Maxima and minima are the plural forms of the words maximum and minimum. Now the same is true for absolute minimum values of a function and absolute or local minimum values of the function. So this y value down here is the absolute minimum value of the function, and this value are local minimum values of the function. So pretty easy ideas here. But there are a few complications when it comes to the terminology and the definitions. So we're going to discuss that with some practice problems. Also, we're assuming that this graph does not turn and go up and down like so, because then obviously this y value would not be the absolute maximum value. We're assuming that the graph proceeds as the arrows indicate in that direction on both sides. So let's do some practice problems. It says write the x value where each maximum or minimum occurs. Assume that the direction of each graph continues as indicated outside the window. Again, we're assuming that this graph goes down as the arrow indicates. The graph doesn't go up and cause a maximum value to occur somewhere unexpected. So we need to find the location of the absolute maximum value of this function. So remember, maximum values and minimum values are y values of the graph. So which point on this graph has the biggest y value? Well, obviously that's this point here. So the absolute maximum value of the function occurs at x is equal to 1. With calculus, the x values are considered to be the locations of things. whereas the y values are considered to be what we call the values of the function. Now, is there an absolute minimum value of the function? And the answer is no. There's no point that you can find on this graph where you can say that its y value is the smallest y value, because the graph just keeps going down. If you choose some point, there's always going to be another point lower than it that has a smaller y value. If you choose this point, well, there's another point farther down that has a smaller y value. So there is actually no absolute minimum value. I'm just going to write the symbol for the empty set. Is there a local maximum value? Yes, there is. This point has a y value that's bigger than the y values of the points around it. So we call that a local maximum value. Now, it's not the absolute maximum value, but the y value is bigger than the y values of the points around it, so we call it a local maximum. Now, remember, an absolute maximum value is also a local maximum value. So not only is there a local maximum value at x equals 4, there's also a local maximum at x is equal to 1. Absolute maximum values can also be local maximum values. That's not always the case, but in this case it is. You'll see that when we have an absolute maximum occurring at an endpoint of some finite interval, those points cannot represent local maximum or minimum values. We'll explain why that is later on. Okay, so is there a local minimum? Yes. This point here has a y value that's smaller than the points, the y values of the points around it. So we call that a local minimum. Again, there is no absolute minimum, but there's a local minimum. So again, we're describing where these values occur by writing the x values. The x values tell you where they are. Now let's move on to the pink graph, the pink function. Is there an absolute maximum value? And the answer is no. Now this is very strange, because a lot of students would say, wait a second, what about this point up here? That point has the biggest y value. Well, it's a hole, so that point doesn't count. Now you might say, well, so what? We can find a point that's really close to it, and we'll just make the y value of that point, we'll make that the absolute maximum. Problem is, if you choose that point, there's actually another point that is closer to that empty dot there. And if we choose that point, then there's another point that's closer to the empty dot. And there's another point that's closer. You can just keep getting closer and closer and closer, but there's always a point that is closer to the empty dot that has a bigger y value. So is there an absolute maximum value of this function? No, there's not. Now, I know what you're going to say. You're going to say, that's weird. I don't know about that. That's weird. And you're right, it is. There's some strange things to think about in the calculus curriculum. And that's an example of that. Is there an absolute minimum value of the function? Yes, there is. This point has the smallest y value, so there's an absolute minimum value of the function at x equals 2. Is there a local maximum value? Now here's where things get strange. Is there a local maximum value of this function? Is there a y value, or is there a point on the graph that has a y value that's bigger than the y values of the points around it? You might say, well, yes, this is a local maximum here, or this point has a local maximum. But this is actually not considered to be a local maximum. Now, why is that? Well, mathematicians consider a y value to be a local maximum if there are points to the right and to the left of it, both to the right and the left, that have y values that are smaller than that y value. But in this case, when you have a point that's an endpoint of some finite interval, well, in this particular case, we have points to the left of that point that have smaller y values, but we don't have points to the right of that point that have smaller y values. So this endpoint is actually considered to not be a local maximum value. And again, I know what you're going to say. You're going to say that's just weird. But that's just the way that mathematicians define things. And the reason they define it that way is it makes the terminology that they use easier, I guess. I don't necessarily agree with their definition of a local maximum value or minimum value, but that's just the way that they do it. Is there a local minimum value? You might consider this to be a local minimum, but again, that's an endpoint. So we don't consider that the y value of this point here to be a local minimum. Now, let's say that the graph, let me modify the graph with a blue curve. Let's say that the graph went like this. It was actually connected. Then this point would be a local minimum. But because we don't have a connection there, because this is an endpoint of an interval, that's not considered to be a local minimum. It's kind of annoying to think of it that way, but that's just the way that they do it. So let's go on to this next purple function. Is there an absolute maximum value? A lot of students would say, yeah, there's two absolute maximum values, here and here. But remember, an absolute maximum is a y value of a function. These points both have the same y value, so there's one absolute maximum at x equals 1, and there's the same absolute maximum located at x is equal to negative 3. Again, it's the same maximum value, but it occurs at two different places. Is there an absolute minimum value? No, there is not, because we have a hole there at the very bottom. If that point were a closed dot, then yes, that the y value of that point at the very bottom of the parabola, that would be the absolute minimum. But since there's a hole there, there is no absolute minimum. Now again, let's explain why that is. Let's say that you have a point that's really close to that point. You might say, well, that point has the smallest y value, but it doesn't, because you can just keep getting closer and closer to that empty dot there. Whatever point you choose, no matter how close to that empty dot, there's always a point that you can choose that is closer to the empty dot that has a smaller y value. So there is no absolute minimum value of the function. Is there a local maximum value? The answer is no. Now you might say, well, what about this? That's these points are local maximum values, but if you choose some point on that line, all the points around it have y values that are the same, so it's not really a local maximum value. Now again, you might say, well, what about these points? You said that absolute maximum values can also be local maximum values. That's correct, sometimes. But in this case, these points, they're the endpoints of a finite interval, and so those cannot be local maximum values. are there any local minimum values? And the answer is no on that also. So again, the concepts here are very easy in a way, but there's also some technicalities in the way that mathematicians define things. So I'm sorry that this is a little complicated, the way that mathematicians define these things. But it's just what we have to deal with. Is there an absolute maximum value of this function? And the answer is no. There is no point that you can choose on this graph that has a y value that's bigger than all the other y values, because there's always a point that you can choose. For example, let's say that you choose a point up here. You might say, well, that point has the biggest y value, but the graph continues. It just keeps going and going. So there's always another point that you can choose that has a bigger y value. So there is no absolute maximum value of the function. For the same reason, there's no absolute minimum value of the function. And there's no local maximum value and no local minimum value. So let's move on to this red function. Is there an absolute maximum value? Well, no, there's no absolute maximum, because this is a hole. Choose a point that's really close. Well, you can always choose a point that's closer to that empty dot. You can always choose a point that has a bigger y value. Same thing is true for absolute minimum values. And there's no local maxima or minima. Okay, let's move on to this orange graph here, the orange function. Is there an absolute maximum value of this function? In other words, we're looking for the biggest y value. Is there one y value that you can say is the biggest y value of the graph? And the answer is yes. This point has the biggest y value that occurs at x is equal to 0. Is there an absolute minimum value? The answer is yes. Again, this point has the smallest y value that occurs at x is equal to 3. Is there a local maximum value? Well, the absolute maximum value is a local maximum, so we can say at x equals 0 there's a local maximum. But we can also say at x is equal to 4 there's a local maximum. This point has a y value that's bigger than the y value of the points around it. It's not the biggest y value, but it's a point that has a y value that's bigger than all the y values around it. Now you might say, well, what about this point over here? That's a local maximum, right? Well, no, that's an endpoint. Endpoints are not allowed to be local maxima or minima. Is there a local minimum value? The answer is yes. There's actually two points that have y values that are local minima. So that point is at x equals -2, and the other point is at x is equal to 3. Now this point had the absolute minimum value, but it's also a local minimum value. Remember, an absolute minimum or an absolute maximum can be also local maxima and minima, as long as they're not located at the end point of an interval. So there you go. Go ahead and take a picture of all this information, and I want you to try some of those problems now. I want you to attempt number 7. So remember, absolute maximum values, absolute minimum values, local maximum values, local minimum values, we're all referring to the y values. Those are y values of the graph. But we want to know where those y values occur. when we say where, we're talking about the x values. So you want to write the x values where these special numbers, the values of the functions occur. So try number 7. When you come back, we'll do it together. Okay, we're back. So now if you're having a little trouble with this because of the definitions and just the way that mathematicians have decided to define things, that's okay, that's normal. But the important thing to understand is we're talking about the biggest y values and the smallest y values of functions. So go ahead and try number 8. When you come back, we'll do it together. Okay, we're back. So again, I know these are kind of tricky, but that's just the way mathematicians have defined these things. It's kind of annoying, I know. Try number 9. If you got number 8 right, good job. When you come back, we'll attempt number 9 together. Okay, we're back. Okay, so if you got that right, good. If you're having a little trouble with this, that's completely fine. It's just the terminology and the definitions is kind of confusing, so you'll get used to this as we go along. Go ahead and try number 10, and when you come back, we'll do it together. Okay, we're back. All right, so if you got that right, good job. Go ahead and try number 11. When you come back, we'll do it together. Okay, we're back. Now again, you might say, well, wait a second, there's also a local maximum here because absolute maximum are allowed, they can be local maximum. That is true, but not in the case of an endpoint. So I'm not trying to overcomplicate things here. This is just the way mathematicians have defined these things. They've taken something that is fairly easy, and unfortunately they've made it more difficult. I know that's annoying. But if you got that one right, excellent. Let's double check that. Everything looks correct. So go ahead and try the orange function. And when you come back, we'll do it together. All right, we're back. Okay, so that helped you to just kind of get the idea of what these terms refer to. But now we're going to learn how to find maximum and minimum values of functions using calculus. As I mentioned at the beginning of the class, this is the most important application of calculus. In this example, we want to find the local minimum and the local maximum values of the function. And this is the function here, and its graph is drawn over here. So here's how we use calculus to find the maximum and minimum values of a function. Now, we learned in previous classes in this course that the derivative is the slope of the line that is tangent to the graph at some x value. For example, let's say that I choose this point right here. The derivative of the function gives you the slope of the line that is tangent to that point on the graph, right? So if I plug in x is equal to -5, it looks like 1, 2, 3, 4, 5. If I plug in -5 to the derivative function, it gives me the slope of this purple line. Now let's say that I move that point up, and now I want to find the slope of the line that's tangent to the graph at that point. Well, I've drawn little segments that kind of represent the tangent lines, but it's only a part of a tangent line. And notice what happens to these little segments that represent the lines tangent to the graph, as we get closer and closer to this highest point on the hill, notice what happens to the tangent line. At the very top of the hill, the line that is tangent to the graph of the function is actually horizontal. Now that's very important because remember, the slope of a horizontal line is 0. Very, very important to remember that. The slope of a vertical line is non-existent. So let's say you have a line that is going straight up and down. The slope is actually undefined. But if you have a line that is horizontal, the slope of that line is actually 0. Do you remember that from previous classes? So at this point here, at the top of the hill, the tangent line is horizontal and its slope is 0. So what we can do is we can find the derivative function, and we can set that derivative function equal to 0. So this is the original function. We're going to find the derivative, and we simplify and get to this expression here. Then we're going to set that derivative function equal to 0, and we're going to solve for x. And guess what we find? We find that if x is -2 or 3, then the derivative function is equal to 0. So when you look up at this graph, guess where the top of this hill occurs and the bottom of this valley? They occur at those exact x values. So the top of the hill occurs at x is equal to -2, and the bottom of this valley occurs when x is equal to +3. So this is how calculus is used to find the locations of maxima and minima, and we can also actually find those y values if we plug in these x values into the original function. So we used calculus to help us figure out where this maximum value occurs. Now these are local maxima and minima. Notice that we're looking for the local maxima and minima, because there actually is no absolute maximum and minimum value for this function, because the function just keeps going down, 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 and it keeps going up and up and up forever. So calculus helps us to find the locations of these maxima and minima. So we know that they occur at x is equal to -2, and we know that they occur at x is equal to 3. But we haven't actually found the maximum value or the minimum value in these regions. We just found where they are. Is that clear? We only found where they are. So in order to find what the actual local maximum value is, the top of this hill, and the local minimum value, the bottom of this hill, we have to take those x values that we found, -2 and 3, and we have to plug it into the original function to find the actual y value of that point and the y value of this point. Those are the actual maximum and minimum values of the function. So when we do that, we plug the numbers back into the original function, and we get the local minimum and the local maximum values. So if we were to write the coordinates of these points, that point there and that point there, the coordinates of this point would be -2, 1 and 5/9, and the coordinates of the other point, this point down here, would be 3, comma, -1 and 1/12. All right? So that's the main idea. That's how calculus is used to find maximum and minimum values of a function, whether they be local or absolute maxima or minima. In some cases, the absolute maxima and minima occur at endpoints, so we don't really need calculus in that case, depending on the context. So here's a situation where we can actually find the absolute maxima and minima of a function. But we do need to use calculus because there's a risk that there may be some other values that could be bigger or smaller than what we consider to be the absolute maxima or absolute minimum. So this problem says on the interval -5, 4, notice it's giving us a finite interval now. On the interval -5, 4, find the absolute minimum value and the absolute maximum value of the function from example 1. So now we have the same function that we had before, and we used calculus to find these pink points. We found the coordinates of the point on the top of the hill, and we found the coordinates of the point at the bottom of the valley there. So we already did that work, but we're dealing with a finite interval. Or instead of calling it a finite interval, you could say that it's a bounded interval. These terms don't really make a lot of sense. They're kind of redundant, I guess. The only reason we're calling it a finite interval is because you can have an interval that is not really an interval, as we encountered in the previous class. A finite interval is an interval where the numbers are obviously not they're not infinity, even though infinity is not really a number. So in this case, there's going to be an absolute minimum and an absolute maximum value. Now, notice these purple lines. Those are where the interval stops. So these blue parts of the graph don't even count. We just cut off those blue parts of the graph. We don't care about those. So what we want to figure out is which point, because we're looking for the absolute minimum value of the function and the absolute maximum value of the function. We're looking for the point that has the biggest y value and the point that has the smallest y value. We couldn't do that over here in the previous problem because there was no biggest y value or biggest or smallest y value, because the graph just keeps going up and up and down and down. But in this case, we've limited the graph. So the graph doesn't just keep going up and up and up, because we don't care about, again, the blue part of the graph or the part of the graph at the left that's going down, 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 down. So we're interested in this orange point, which is an endpoint, and this blue point, which is an endpoint, as well as the point that's at the top of that hill and the point that's at the bottom of that valley. So there's 4 points that we're interested in. And so what we have to do is we have to check the endpoints. So you see this orange point here, we're going to plug in -5 for x into the original function. We do the math and we end up with this number here. Then we plug in 4 to the function. You see the blue point up here? We're going to plug in 4 to the original function. So I did that down here. And we end up with -1 and 4/9. So now we have these 4 points. And again, we don't care about the blue parts of the graph. Those parts don't count anymore. So of all the points that are in this orange interval that we're analyzing here, which point has the biggest y value? Well, that would be this point, obviously. So the absolute maximum value, in the previous problem we couldn't find an absolute maximum value, but now we can. The absolute maximum value on this interval is 1 and 5/9. The absolute minimum value is -3 and 25 36. That's the absolute minimum value of the function on this interval, because it's the point that has the smallest y value. So notice that the absolute minimum value actually occurred at an endpoint. So long story short, when you have an interval, a finite interval, when you have bounds, you can actually find the absolute maxima and the absolute minima of functions. Okay, so there's something called Fermat's theorem that tells us if a function has a local maximum or a local minimum at x equals some value, and the derivative at that value exists, then the derivative must be equal to 0. So that's what we learned with this problem. Remember, we set the derivative equal to 0, and we found the x values where these maximum and minimum values occur, whether they're absolute or just local. That's how you find the values of the function at the tops of hills and the bottom of valleys. We have to use calculus for this. So Fermat's theorem is just a way to kind of state the obvious. You want to find the maximum values and the minimum values, you have to find the derivative of the function and set it equal to 0. Or you can sometimes find the absolute maximum value or the absolute minimum value of a function at endpoints, but again, this is talking about local maximum and minimum values. Now, notice it said here that the derivative at that particular x value has to exist. Fermat's theorem only applies if the derivative exists. And again, Fermat's theorem is telling us that the derivative here and here is 0. We have to set the derivative equal to 0. So that's what Fermat's theorem is talking about. Most students don't really remember Fermat's theorem. They just remember the concept. So if you don't remember this theorem, that's not really a big deal. But again, this theorem only works if the derivative exists. When can we have a maximum value or a minimum value of a function where the derivative doesn't exist? Well, we talked about those situations in the previous class. Here, notice that this point is it's actually a point that has the absolute maximum value of the function. The y value of this point is the absolute maximum value of the function. But the derivative at that point is not equal to 0, because remember from the previous class, the derivative at that point is actually undefined. So a maximum value of the function is located at x equals -2, but the derivative is not equal to 0. So Fermat's theorem doesn't work when you have a kink in the graph. Same thing here with the absolute value function. So this brings us to an important definition: critical numbers. What are critical numbers? Critical numbers are x values where the derivative of a function is 0 or undefined. So if you're trying to look for the maximum values or the minimum values of a function, what you do first is you find the critical numbers. So the derivative is undefined here, so that might be the location of a maximum value, and it turns out it is. The derivative at x equals 0 down here is undefined also, and that might be the location of an absolute minimum, and turns out it is. So critical numbers are numbers where special things happen. Over here, we had a local, actually that was the absolute maximum in the case where we have bounds, and the derivative was equal to 0. So again, that's x equals -2 is a critical number. Over here, when x was 3, the derivative was 0. So x equals 3 is a critical number of that function. So these numbers that we found using calculus, those are critical numbers. So again, critical numbers are x values that make the derivative undefined or equal to 0. So we're going to talk more about that as we go along here. Now, the locations of regions of interest of the graph of a function are described with x values, as we talked about previously. And the x values are often written in interval notation, and we talked about interval notation in the previous class. So there's a lot to kind of take in here today. A lot of terminology and things, but we're going to get some practice with this so you understand what we're doing. There's a theorem that I'm calling the critical number theorem that says that if a function has a maximum or minimum value, then the input where that value occurs is a critical number. So this is a really fancy theorem, but all it's saying is that if you want to look for maximum or minimum values of a function, those values are going to occur at the critical numbers. So what this means is you need to find where the derivative is equal to 0, and that might be where a maximum or minimum value occurs. You also need to find where the derivative is undefined. That might be where a maximum or minimum occurs. But just because the derivative is undefined at some x value, or the derivative is 0 at some x value, that does not prove that there's a maximum or minimum value there. So be aware of that. It's like saying, if you're trying to look for a fish, let's say you want to catch a fish, you know that the fish are going to be where there's water. Wherever there's water, there might be a fish. But just because there's water doesn't mean that you know for sure that there's going to be a fish. Well, that's kind of what this is saying. If you want to look for maximum and minimum values of a function, you know that they're going to be at the critical numbers, the numbers that make the derivative of a function undefined or 0. But just because you find a critical number doesn't mean that a maximum or minimum value is going to occur there. So here's some examples where critical numbers are present but no maximum or minimum values occur. So notice that this special point here, if you draw the line that is tangent to the graph of the curve at this point, that line, it may not be easy to see, but that line is actually horizontal. So x equals -2 is a critical number because the value of the derivative at that point, -2, is 0. But does this look like a maximum or minimum value? Does the y value of this point look like a maximum or minimum value of the function? The answer is no. Here's another example. When you have an asymptote, the derivative is actually undefined when x is equal to -1. This is the original function, but if you find the derivative and try to plug in -1, you'll get an undefined expression. So x equals -1 is what we call a critical number, but that doesn't mean that there's a maximum value or minimum value here, because the function is not even defined there. There is no maximum or minimum value at that asymptote. Here's an example where we have a piecewise function. At x equals 0, we have a critical number because the derivative is not defined when x is equal to 0. So the derivative doesn't exist. But there's no maximum or minimum value at x equals 0. You might say that this point here is a local minimum, but again, local maxima or minima cannot occur at endpoints. So we mentioned previously, but I'll say again, that when you talk about the values of a function, you're talking about the y values of the function. so just be aware of that. We talked about describing regions of interest with intervals. The intervals that we discuss in this entire course are always x values. When you talk about intervals, you're talking about x values. X values tell you the location of things. They tell you where things are. They tell you the regions of the graph that we're talking about. X values are used to indicate location. The values of the function are the y values of the function, but the locations of these y values are considered to be the x values. Now we have some more special terms here. A closed interval is an interval that includes all of the x values between a and b, as well as a and b. So a and b are part of the interval. That's why we have brackets. An open interval is an interval where we have all the values between a and b, but not including a and b. We call that an open interval. Now you might wonder why these terms, open and closed, are used. I'm not really sure, to be honest with you. That the terminology doesn't really make a lot of sense. But that's just the terms that they use. So here's an example of a closed interval. Notice that we have those dots as endpoints, as opposed to here where we have an open interval and there's holes at the endpoint. So that's an open interval. So I know you're probably thinking we're making things too complicated here, but this stuff is going to be important as we move along. Now we've been referring to maxima and minima, maximum values, minimum values. You can use those words as nouns or adjectives. If you say, I want you to find the maximum of a function, you're using the word maximum as a noun. It refers to the biggest y value. But if you say, I want you to find the maximum value of the function, maximum is being used as an adjective. So just be aware of that. But we also use the word or the phrase extreme value. An extreme value is just a maximum or a minimum. And the plural form of that is extrema. So just be aware of that. We use the word or the phrase extreme value to refer to maxima or minimum. The word extreme usually refers to absolute maxima and minima, but sometimes it can also refer to local maxima and minima. Now we have something called the extreme value theorem that tells us that if a function is continuous on a closed interval, meaning the endpoints are not holes, that would be in this case over here. If a function is continuous on a closed interval, like what we see here, then the function has an absolute maximum and an absolute minimum at some x values in a comma b. So when we say the maxima and the minima occur in a comma b, we're talking about those values occurring in that interval. So for example, this would be a, and whatever this x value would be, that would be b. So in that interval, there must be an absolute maximum and an absolute minimum. That's the extreme value theorem. So we'll have plenty of time to go back over this. I know I'm kind of throwing a lot at you at once, but there's a lot of terminology that you have to know in calculus. And that's what makes this part of the course a little tedious, is having to learn all this terminology. Now there are situations where there are no absolute maxima or minima, as we discussed. The extreme value theorem tells us that absolute maxima and minima occur, but we found out that you have situations where there are no maxima and minima. So that's these situations here. But we also saw situations where we have no local maxima and minima, or absolute maxima or minima. So that's these situations. Okay, so now we're going to learn a theorem for finding the absolute maximum or absolute minimum of a continuous function on a closed interval. It turns out that if a function is continuous on a closed interval, then the critical numbers and or the endpoints are the locations where the absolute maximum value and the absolute minimum value of the function can be found. So the extreme value theorem tells us that those absolute maxima and minima do occur. They have to exist. But this theorem tells us actually how to find the absolute maxima and minima. So I want you to be aware of something, because I know you're probably getting kind of nervous, thinking, there's a lot of stuff that we've introduced here. We got Fermat's theorem that tells us that we can set the derivative equal to 0, because the tangent line is horizontal at maxes and mins. We've got that theorem called Fermat's theorem. We've also got the critical number theorem. We've got the extreme value theorem. How am I going to remember all this? Well, the truth is, students don't really think about Fermat's theorem, the critical number theorem, or the extreme value theorem. They don't even know what the names of those theorems are, and you're not really required to know either. All you're required to do is know how to use the calculus and what a critical number is, what an extreme value is, maxima and minima and all that, and how to find the locations of these extrema, these extreme values. So everything that we talked about previously in the first hour of this class is just terminology. We talked about a few concepts, but most of that was just terminology. So that's why this part of the course is kind of tedious. You have to learn a lot of terminology. But now we're going to actually find out how this actually works. So let's get started. We're going to use this theorem, and you don't have to remember the name of the theorem. The name is kind of long, obviously, but you do have to remember the principles of this theorem and know how to use it. So this theorem is really the main thing that we're going to be using today. The other theorems are just stating things that we need to proceed with these concepts. So we're going to use this theorem to help us do the following problems. It says find the absolute maximum and the absolute minimum of each function on the specified interval. And I want you to get your graphing calculator. The graphing calculators are going to help us understand the concepts that we're about to learn. And it's also going to help us to do some tedious calculations. So what this problem is asking us to do is to find the biggest y value of this function between x equals -4 and x equals 1, inclusive. You can also think about it as finding the biggest output of the function when x is between -4 and 1, inclusive. So in order to do this, we're going to, well, we don't really need the graphing calculators to solve this problem, but we're just going to use them to help us understand the general concept of this theorem here. So I want you to get your graphing calculator, and I'm going to demonstrate how to use the TI-84 Plus. If you have a different calculator, you're going to have to figure out how to use that on your own. So at the bottom left, push the on button, and then I want you to push the y equals button at the upper left, the stat plot F1 button, the y equals button. And if there's an equation, press the clear button at the middle upper right. And then I want you to push this button, the x comma t comma theta comma n button, and I want you to enter this expression in there, and use the upside down V button at the right to enter exponents. So I'm going to enter that into my calculator also. So we should have x to the fourth power. And by the way, you want to use the arrow keys, the right arrow key specifically, to move to the right as you enter that in. Now if you have some problems, that's okay. If you make a mistake, you can clear that or delete and fix the problem. It takes some practice to enter these expressions into the calculator. So you should have x to the fourth power plus 4x to the third power plus 4x to the second power. So you can stop the video and make sure you have that entered in. So now I want you to press the window button at the upper left next to the y equals button, the F2 table set button, the window button. And the problem with graphing using the typical graphing calculators that are used in school is that when you graph, oftentimes your window is not really a good window, and so you have to regraph, and you may have to do it a number of times, and it's very annoying. But in these particular problems, we're given the horizontal window. So I'm going to enter -5 for x minimum and +2 for x maximum, because I want my window to be a little bit bigger so we can see what's going on. And for y minimum, I'm going to enter -10, and for y maximum, +10. We don't really know what the vertical window should be, but I'm just going to guess. So then at the upper right, I want you to push the graph button, the table F5 graph button at the upper right. And your graph should look something like, let me move this over, should look something like this. My graph is not perfect, but something like that. And we're only interested in the parts of the graph from x equals -4 to x equals 1. So what that means is we don't care about these blue parts of the graph. We're just cutting that off and ignoring it. We're just interested in the yellow part of the graph. So again, what we're trying to find is the points that have the biggest y values, the points on the graph that have the biggest y values in this yellow interval. So again, what we want is to find the biggest y value of the graph on this yellow interval and the smallest y value of the graph on this interval. So we need to find the points on the graph that have the biggest y value and the smallest y value. Now, this theorem up here tells us that if we have a continuous function on a closed interval, meaning brackets, and this is continuous because we don't have any fractions with variables in the denominator or logarithms or square roots. If we have a continuous function on a closed interval, then the points that are the possible candidates that we're interested in are the endpoints and the points that correspond to what we call the critical numbers. So these are the endpoints, and these are the points on the graph at the critical numbers. So what that theorem tells us is that one of these circled points, the points that I just circled, has the biggest y value, and one of the points has the smallest y value. And in this case, there's actually more than one point that has the smallest y value. So we can see what the minimum value of the function is. The minimum value obviously is going to be 0, because these 2 points have y values that are equal to 0, right? And we can see which point has the biggest y value. That's this point over here. But you have to use calculus to show all this is correct. Again, we're not using the graphing calculator to avoid using calculus. You have to know how to use the calculus. We're just using the graphing calculator to help us with the main concepts. So now we don't need calculus to find the y values of these points here, but we do need calculus to find the y values of these points, because we don't know necessarily where those points are. So we have to find this x value, and this x value. Now, of course, we probably suspect that that's 0, but we don't really know for sure. It looks like it's 0. Now, this is where calculus comes in. And by the way, why is it that these are possible points that will have the smallest y values or the biggest y values? Well, because they're points that are at the tops of the hills and at the bottoms of the valleys. That's why we have to check those points. Now, remember, if you choose some point on the graph, this line is the line tangent to the graph, and the slope of that line is the derivative. Now, what happens as you bring a point closer and closer to the bottom of that valley? Well, what happens is that the tangent line actually levels off, and at the bottom of the valley, the tangent line is actually horizontal. If the tangent line is horizontal, then that means the derivative, which is the slope of the tangent line, the derivative should be 0, because the slope of a horizontal tangent line is 0. The same is true up here. When we get closer and closer to the top of this hill, our tangent line starts to level off. That's the line tangent to the graph at that point. And then when you get closer and closer, the tangent line starts to level off. Sorry, my computer's going kind of slow. So it's leveling off, you see that? And then when you get to the top, it's horizontal. So that means that the slope of the tangent line when you get to the top of that hill is going to be 0. So remember, the derivative is the slope of the line that's tangent to the graph. And so what we have to do is find the derivative, and then we're going to set it equal to 0, and then solve the equation, and we're going to find these x values where the slope of the tangent line is 0. Then we're going to plug those x values into the original equation and find the corresponding outputs, the y values, so we can compare those y values to these y values. The biggest y value is going to be the absolute maximum, and the smallest y value is going to be the absolute minimum. Now, I know what you're thinking. You're thinking, whoa, that was a lot of stuff. That's complicated. Well, the concepts are really not that complicated, but the process is a little long-winded to have to explain it. So I'm sorry about that long-winded explanation, but this is the main application of calculus, so we're going to do this a lot in this course. Okay, so we need to find those green x values. Those x values are where the derivative is 0, but first we have to find the derivative. And set it equal to 0. So we have the derivative, and by the way, those special x values, again, they're called critical numbers, where the derivative is 0 or undefined. Now, the derivative is not going to be undefined for this particular function, but it is going to be equal to 0 at certain x values. So we're looking for the critical numbers, these green x values that make the derivative 0. So we have to solve the equation. And now we factored out GCF, and we factored a quadratic expression. Now, if you have never done that before, that means you're in the wrong course. or it just means that you didn't learn what you were supposed to learn in previous courses. And that may not be your fault, but nonetheless, you're not going to be able to continue. I can only guarantee you that my curriculum is going to teach you what you need to know. I can't guarantee that any other curriculum is going to do that. Although there are a lot of good curricula out there, but there's a lot of bad curricula out there too. So again, if you don't know how to do this, then that suggests that there's a problem. Okay, so now we have the critical numbers. We have these green x values. And I want you to notice that x equals 0 corresponds to that valley. X equals -2 corresponds to this value. And x equals -1 corresponds to this valley. So that's the power of calculus. So now we have to find the y values of these points. So we're going to plug in these critical numbers to the original function. And I've rewritten the original function here. So first let's plug in 0. And then let's plug in -1. And so that was pretty easy, but if we try to plug in -2, we're going to find that the calculation may be a little bit more difficult. Now, I want you to understand that you don't have to show this stuff here. All you have to show is what you're finding and the answer. I'm only showing this highlighted stuff here because I want you to see what I'm doing. But you students, you really don't have to do that. It's just too tedious to have to write all that out. Okay, so I want to show you a trick that you can use on your calculator to find this value without having to do it in your head or on paper. So I want you to turn on your calculator at the bottom left, press the on button, and understand that we have this equation in the graphing part of the calculator. The buttons at the top are for graphing. So I want you to press the blue second button at the upper left, and then the trace button at the upper right, the calculate F4 trace button at the upper right. And you see where it says value on number 1? Press enter and see how it says x equals. At the bottom right, press the negative symbol with the parentheses around it, and then the 2 button, and then press enter. You should have x equals -2, and see how it says y equals 0 at the bottom right? That means that all of this actually equals 0. Okay, so that's a good way to avoid having to do all those calculations. So these are all the y values of those middle points. See these middle points here? So now we need to compare those points, or those y values, with the y values of the endpoints. Again, that's what our theorem tells us, is that the absolute maximum y value and the absolute minimum y value are going to be the y values of these points. One of those points is going to be the max, and one of them is going to be the minimum. There could be more than one point. For example, these 2 points they both produce an absolute minimum. But so we're going to check the endpoints now. We're going to check these points. We haven't checked those. So these x values over here are the x values of the endpoints. So we're going to plug in 1. and we get 9. But I want you to practice on your calculator doing these calculations so that you know how to do that for your homework. So I want you to press the blue second button at the upper left, and then the trace button, the calculate F4 trace button at the upper right. Then press enter on value, and then enter 1. X equals 1, and then press enter, and it should say y equals 9 at the bottom right. Now we need to plug in the x value of the other bound, so -4. And this is really going to be difficult to calculate, for most students to calculate. So this is an example where you want to use your calculator. So press the blue second button at the upper left, then the trace button at the upper right, the calculate F4 button. Press enter on value, and then enter in -4 using the negative symbol at the bottom right with the parentheses around it. Press enter, and it should say y equals 64 at the bottom right. So I want you to look at these red values, these values highlighted red. The red values down here are the middle, are corresponding to the middle points. They're the y values of those middle points. The y values here are corresponding to the y values of the endpoints. And what this theorem up here tells us is, again, that the biggest y value has to be one of those 5 red points, or it has to be one of those 5 red values. The smallest y value has to be one of those 5 red values. So you can see that the biggest value is 64. So that corresponds to this number here. My graph is not drawn perfectly, but the absolute maximum value of the function on that interval is 64. The absolute minimum value of the function on that interval is 0, because that's the smallest value. Notice that there's 2 x values that produce the absolute minimum. Sometimes that happens. You can have multiple x values that produce the same absolute minimum. So that's how this works. So I know that that's a lot, but once you get the hang of this, once you understand how to do this, it's really not difficult. So let's try another problem. So I want you to enter this into your calculator, and again, what we're trying to do here is we're trying to find the biggest y value of this function between x equals -1 1/5 and x equals 1/10. What is the biggest output of this function between the x values -1 1/5 and 1/10? Inclusive. We're including the actual bounds themselves because we have brackets. So probably the easiest way to enter this into your calculator is using exponential notation. So like this. And when we do our calculus, we're going to use the exponential notation to find the derivative. But I want you to know how to enter this in using root notation also. So press the y equals button at the upper left, the y equals button, the stat plot F1 button, and then press clear at the right. And again, you can use the upside down V button to enter exponential functions if you want. But you can also press the math button at the upper middle left. Press the math button and go down to number 5, the x root. Press enter, and you should have this template here. Alright? And enter 3, and then you're going to have to use the right arrow key. Very important to use the right arrow key. You want to make sure that you're out of the root when you write these expressions or enter the expressions in your calculator. So use the right arrow key, and of course use the x, t, theta, n button for your variables. And again, use the right arrow key, press the math button again, go down to number 5, and enter this whole thing in here. Don't forget to write your +3, or enter your +3 into the screen. So we should have the cube root of x squared plus the cube root of x to the 5th plus 3. Now press the window button at the upper left next to the y equals button. And I want you to enter this horizontal window, but I'm going to enter -2 for x minimum and 1 for x maximum. Now, I designed this problem, so I'm going to show you the best vertical window also. So enter -1 for the y minimum and +4 for the y maximum. And then press the graph button at the upper right, the table F5 button at the upper right. So your graph should look something like this. Now, we are interested in the interval from -1 1/5 to 1/10. So that's this yellow region in here. We don't care about the blue parts of the graph. We're going to pretend that they don't exist. So what this theorem over here tells us is that if we have a continuous function on a closed interval, brackets being closed, and this is continuous because we have cube roots, so there's no x value that you can plug in there that's going to make the function undefined. I know that's not exactly obvious that that's a continuous function, but I'm only going to give you continuous functions in this class today for these particular problems. So what that theorem tells us is that if we want to find the biggest y value of the function in this interval and the smallest y value of the function in that interval, those y values are going to be y values of the endpoints or y values of the points located at the critical numbers. The critical numbers meaning the x values where the derivative is 0 or undefined. Okay? So we don't need calculus to find the y values of these points, but we do need calculus to find the y values of this point and this point. Now again, the derivative is the slope of the line that's tangent to the graph. So let's say that we draw this green point here on the graph. The line tangent to the graph is that line there. That line has a positive slope. But as we get to the very top, right when we get to the very top, the line tangent to the graph is actually horizontal and its slope is 0. So that means that the derivative is 0 because the derivative is the slope of the tangent line. So what we need to do is find the derivative of this function and then set it equal to 0 and then solve for x, and that'll give us these special x values. So it just so happens that this x value is 0 like in the previous problem. That was just a coincidence. But what is the point that has the biggest y value? Well, it seems like it's going to be this point. I don't know for sure. My graph is not completely accurate. And what is the y value that has or what is the point that has the smallest y value? Well, it seems like it's going to be this one, but I may not have drawn my graph properly. It might be this one. So we're going to use calculus to figure it out. So we're going to find the derivative of the function. Derivative of 3 is 0. Now, we don't know how to interpret that expression, so we're going to use exponent rule number 8 to bring that negative exponent down, and exponent rule number 10 to change 2/3 power to the cube root of x squared. Then we're going to use exponent rule number 9 to change that x to the 1/3 power to the cube root of x. Now, if you don't recognize this type of math with these exponents, if you don't know these exponent rules, again, that suggests a problem. That means that you probably did not receive adequate instruction in your previous courses. Okay, so we have the derivative now, but the reason we found the derivative is we want to find these special green x values where the derivative is 0 or where the derivative is undefined. And it turns out that we have a sharp turn here, so the derivative is going to be undefined at x equals 0. Now, when trying to analyze the derivative function for critical numbers, I want you to understand that in most cases it's best to combine the terms into one expression. I know that that's not exactly convenient, but in my experience that's the best way to easily see where the or what the critical numbers are. We want to know where this derivative is 0 or undefined. Now we know that when x is 0, that makes 0 in the denominator. So again, we can kind of see that when x is 0, the function is not going to be differentiable, meaning the derivative is not going to be defined. But we're going to combine these terms by getting a common denominator so we can see easily where the derivative is 0 and where it's undefined. So we're now going to use this rule, the nth root of a times the nth root of b is equal to the nth root of a times b. Now, you may be a little rusty on that, but if you've never seen it before, that suggests that there's a problem. So we're going to put these two together, so it's x squared times x. And then we get we get 5 times the cube root of x cubed. Now, what is the cube root of x cubed? Well, obviously that is just x. Alright, so that became x. Okay, and we have a common denominator, so we can combine those terms. And so now we have 2 plus 5x over 3 times the cube root of x. Now this is the derivative in a form that really helps us to understand where the critical numbers are. We want to know what makes the derivative 0. That's what makes the numerator 0. And we want to know what makes the derivative undefined. That's what makes the denominator 0. So if we solve for x here, we have negative 2/5. And if we divide both sides by 3 and cube both sides, we have x is equal to 0. But that's not really necessary because we know that the only value of x that's going to make that 0 is 0. So if the numerator and the denominator are 0, that's a completely different situation. If they're 0 at the same time, that is. But we don't have that situation here. So I want you to see that x equals 0, that corresponds to this sharp turn in the graph. And x equals negative 2/5, that corresponds to the top of this hill. So we found the critical numbers. Now we need to plug in those green x values into the original function and see what the y values of these points are, and then we can compare, because those y values might be the absolute maximum y values and the absolute minimum y values. We're not sure. We also need to check the endpoints. So we're going to plug in 0. And you can see that we get 3. Then we're going to plug in negative 2/5. These are the critical numbers that we found. Okay, so this is obviously going to be very tedious. So I want you to press the on button at the bottom left of your TI-84 Plus if it turned off. And I want you to press the blue second button at the upper left. And then the trace button, the calculate F4 trace button at the right, and then press enter on value. And then the negative symbol at the bottom right with parentheses around it. And then 2 divided by 5. You should have x equals negative 2/5. Press enter, and at the bottom right you can see we have approximately 3.32573. Alright, so we just found these red numbers are the y values of these two inner points there. 3 is the y value of that point, and 3.32573 approximately is the y value of this point here. But we have to compare those y values with the y values of the endpoints. That's what our theorem tells us. We have to check the endpoints also. So the endpoints are well, the x values of the endpoints are these bounds here. So we have to plug in negative 1 1/5. And instead of writing negative 1 1/5, I'm going to write negative 1.2, because in upper mathematics you don't really use mixed numbers much, because they're inconvenient. So obviously this is going to be a tedious calculation, so we're going to push the blue second button at the upper left, and then the trace button at the upper right, and then press enter on value, and then we're going to use the negative symbol at the bottom right and 1.2, and then press enter, and then at the bottom right we have our approximate value, which is 2.77415. Alright, now we're going to plug in 1/10, but instead of 1/10, I'm just going to enter 0.1. So I want to make it clear that that came from there, and this pink value, that came from there. I'm just using decimals because it's easier to write it. So we have 0.1 squared, 0.1 to the 5th, and so again, this is very tedious to have to calculate. So push the blue second button and then the trace button, and then enter on the value button and enter 0.1, and then enter, and we get 3.2369. Now I'm just going to round off to 9. Okay. So now we have to compare these values. So look at these red values up here and look at these red values here. Now these values are the y values of these points at the end, at the end points. So what is the biggest y value, the biggest of the red numbers? The biggest of the red numbers is 3.32573, and the biggest, or the smallest of the red numbers is 2.77415. So we found the absolute maximum value of the function on the interval, and we found the absolute minimum value of the function on the interval. Okay, so that's how this works. For the endpoints, we don't need calculus, but for the points in between the endpoints, we do need calculus. We have to find the derivative and figure out where it's equal to 0 or undefined. So I want to make it clear, we found the y values of all these special points, and we compared them, and our theorem told us that the biggest y value of those 4 points is the absolute maximum value of the function on this interval, and the smallest y value of those 4 points is the absolute minimum value of the function on this interval. Now I didn't draw this graph right, because this point should actually be lower than the other points, so just be aware of that. We just discovered that that point should be lower, so maybe I can redraw this so it looks more realistic. So maybe it does something like that. See how that point is lower than this point? That's what we just discovered. Okay, now I know you're probably wanting to try one of these on your own, but let's attempt one more of these together. Press the y equals button at the upper left, and then push the clear button at the right, and then the math button, and you can enter a root template, and you're going to need parentheses around 2x plus 1 when you raise to the 5th power. If you don't write parentheses, then it's not gonna work. So the left parenthesis button is right in the middle of the calculator, and the right parenthesis button is right next to it, of course. Now again, when we do the calculus, it's going to be easier to write this as 2x plus 1 to the 5/7 power plus 1. But and you can enter it like this in your calculator also. But make sure you have that in your calculator. Use the right arrow key to make sure you're out of the root. And again, if you make a mistake entering this in, just figure out what you did wrong and fix it. So now let's press the window button, and I'm going to make the x minimum -3 and the x maximum 1, and the y minimum I'm going to make -2, and the y maximum I'm going to say 3, and I'm going to press the graph button at the upper right. And it's hard to see what exactly is going on with this graph. The calculator is not really doing much for us. But what's happening is we actually have a vertical tangent line. And we're interested in this interval, -2 to 0. Which means that these points are going to give us the possible maximum and minimum value, the absolute maximum and minimum. But what you're going to find is that here there's a part of the graph where the line tangent to that part of the graph is actually vertical. And so that's going to be a critical number. Now we can see that this is not the top of a hill and it's not the bottom of a valley, which means that this is not going to be that this point its y value is not going to be one of our answers. But again, if you couldn't graph this and had to just use calculus, we wouldn't know that. So we're going to do all the calculus to show why that critical number is not going to lead to an absolute maximum or minimum. So we want to find the biggest y value in this interval, and we don't care about these blue parts of the graph. So let's find the derivative. We're going to have to use the chain rule because we have a function inside another function, a function inside another function. And I'm going to move this down a little bit. So we found the derivative of the outside function. We kept the inside function, and then we multiplied. Sorry, my computer's going kind of slow. We found the derivative of the outside function. That's the first step, and we kept the inside function, the second step, and then we multiplied by the derivative of the inside function, which is 2. So if we simplify this, we have 5/7 or 5 over 2x plus 1 to the positive 2/7. I'm going to go slow here so you know what's happening. And then that turns into 10. 2 times 5 is 10. 10 over 7 times the 7th root of 2x plus 1 to the second power. Now we can see that nothing is going to make the numerator 0, so the derivative is not going to be equal to 0 anywhere. But the derivative is going to be undefined because, again, we have a vertical tangent line here, and the slope of a vertical tangent line is undefined. So we need to figure out where this derivative is undefined, but we can see that that's just going to be where x is equal to -1/2. That's a critical number. Because if you plug in -1/2, the denominator becomes 0. So I don't really have enough room to really show that unless I get rid of our graph. Maybe I can move our graph up a little bit. So again, we want to set the denominator equal to 0. And the way you would solve that, if you really wanted to do the algebra, we don't have to because we know what x is going to be. We can see what it has to be. But you divide by 7, divide both sides of the equation by 7, and then raise both sides of the equation to the 7th power, and then square root both sides of the equation, and then subtract 1 and divide by 2, and x is equal to -1/2. So again, that corresponds to this value here. So now we're going to evaluate the function at x equals -1/2. So I rewrote the function there. And if we do the math, we end up with 0 plus 1, which is 1. But again, we know that's not going to be the biggest y value because it's not even the top of a hill or the bottom of a valley. So now we're going to check these y values, the y values of the endpoints. So we're going to plug in the x values of the endpoints. So -2 and 0. and we end up with 2. 1 plus 1 is 2. And you can do that on your calculator if you want to. We're also going to plug in -2. It's probably going to be best for us to do this one with our calculator. So you go to this blue second button and then the trace button at the upper right, and then enter on value. And then we're going to enter -2 using the negative symbol at the bottom right with parentheses around it, and then press enter. And then we have -1.1918 approximately. Okay, so these are the y values at the endpoints, and this is the y value at the critical number. And so the absolute maximum is 2, and the absolute minimum is -1.1918. So those red points are the y values of these 3 points. So again, our theorem tells us that the biggest y value and the smallest y value of the function on this yellow interval are going to be the y values of or possibly the y values of these 3 points. If we're going to find the absolute maximum and minimum, they're going to be the y values of some of these points. Okay, so now it's time for you to try. I want you to try number 16, but before you do that, I want you to take a picture of this theorem here and number 13, and I also want you to get a picture of number 14. And I want you to get a picture, well, you can just leave number 15 in the window. So you're going to enter this into your calculator, and let's do that together. So press the y equals button at the upper left, push the clear button at the right, and then the x, t, theta, n button, upside down v button, to the third power, -3 times x, plus 1, so make sure that that's entered in. And so now you've got your equation in there, your expression, but you need to make your window. Before you push the graph button, you need to set your window. So press the window button at the upper left, the table set F2 button, and what do you write for the window? Well, we don't know. We don't know what our window is going to be, but we actually do. This is the horizontal window, so I'm going to enter -4. For x minimum and x max, I'm going to enter 2. And I'm going to enter -5 for y minimum and +5 for y max. So we'll see how that works. So push the graph button at the upper right. And so your graph is going to look something like this. Okay, so now you have the graph in there, and I want you to try number 16. You're going to find the derivative and set it equal to 0, find the critical numbers, and those numbers will give you the locations of the tops of the hills and the bottoms of the valleys. Plug those critical numbers into the function, and then plug the endpoints into the function and compare all the outputs and see which ones are biggest and which ones are smallest. Try number 16. When you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. Okay, so go ahead and take a picture of these problems, and I want you to try number 17. So put this into your calculator. This is going to be your horizontal window but I would choose a window that's slightly bigger. Then you're going to find the derivative, find where the derivative is 0 or undefined, and plug those x values into the original function, and then plug the x values of the endpoints into the original function and see which output is bigger, which y values are the biggest and which y values are the smallest. So try number 17. When you come back, we'll do it together. So if you got that one right, good. Go ahead and try number 18. For number 18, number 14 is going to be very helpful to reference. Remember when we found the derivative and we had two terms. We had this term and we had this term. But we combined the terms to make one fraction down here for the derivative. And if the numerator was 0, that x value that made it 0 was a critical number, and if the denominator was 0, that x value that made it 0 was also a critical number. Now, if the denominator and the numerator are 0 at the same time, that's a different situation, but we're not going to encounter that. So get a picture of number 14. That's going to be very helpful. Also be aware that when you find the derivative of this function, you're going to have to use the chain rule, because we have a function within another function. And even though your interval is -4 to 10, in order to see your graph, I would suggest making your horizontal window -15 to 15. So attempt this problem, and when you come back, we'll do it together. Okay, we're back. So if you got that right, good. That was a pretty challenging problem, so if you had some trouble with that, that's okay. If you did well, then that's very good. Sometimes calculus problems can get pretty tedious and involved, unfortunately, so you do need to see some of these types of problems. So that was the class today. If you'd like to take screenshots of all the work that we did to help you with your homework or to study for tests, go ahead and do that now. Here's screenshot number 1. And here's screenshot number 2. And number 3. And number 4. And number 5, number 6, number 7, and number 8, and number 9, and number 10, but don't go before you get your homework. Remember, the homework is not optional. It must be done completely and correctly and neatly and kept in order in your binder. So here's screenshot number 1 of the homework. And screenshot number 2. And screenshot number 3. And number 4. And number 5. And don't go before you get the answers to the homework. Here's the answers. It's not enough just to attempt the homework. It must be done correctly. So be sure that you get a screenshot of those answers. So get that homework done completely and correctly and neatly, and I'll look forward to seeing you in the next class.